physics. I forgot that was in there. If you get the answer, text it to me.
Morning. Right, on the board is a question from section 8.2. A telescoping theory questions determining the partial sum for this. We're not calculating the summation. We're trying to figure out the way to write S of n. S of n is a summation of the first n term because n is abstract and is a random term in the series, in the summation of the series. So that's what's making it a little bit hard because the answer for S of n is supposed to be a formula. So that's how you come up with a formula for S of n. Here we have 4 answers. I think, well, I recommend try to write from the beginning. You can write a couple examples to see what was the pattern. So for example, if you are not sure on how to derive S of n, you can start by deriving S of 2, S of 3, S of 4. And now you're gonna see the pattern. So for example, right now, if we only calculate S of 2, that's summation of the first 2 terms. So S of 2 would equal to, this is the first term, see K was the index in this case. So 2 over K equal to 1, that's 2 over 1 plus 1 minus 2 over 1. And then, the second term is 2/3 minus 2/2. So you can see when you're adding it, the 2/2 was canceled, your answer will be, -2. This is the only term that was canceled. -2 plus 2/3. Okay, so that's how it looks like when you're calculating S of 2. If you're calculating S of 3, this is how it looks like. S of 3 is equal to the summation of the first 3 terms. So we have 1, 2, 3. And you go through the calculation, realize that again, the term that was canceled still get canceled. That was canceling that term. And then the 2/3 will be canceled by the -2/3. So that was gone. So this one no more. And then you still have that -2 because we don't see any term that is able to cancel it. So you have -2, and then you have that 2/4 right there. So cancel the 2/2, cancel the 2/3, you have the -2 plus 2/4. And you can start seeing the pattern, you can calculate S of 4. So one of the ways, if you are not sure, like which one get canceled, which one is not canceled, because telescope is here, make the middle terms canceled. We want to be sure to know which one was remaining, which one canceled with negative term. S of 4 is going to be summation of the first 4 term, it's all 4. So you can see the one that 2/2 cancel is -2/2, 2/3 cancel is -2, and 2/4 cancel is negative. We have the 45 left. So you can start saying the pattern is -2 plus 2/5. And then if we're asking which one saying to fit the pattern, you can see the pattern, right? Right? Yes, but you have your answer. Okay, so the answer should be we certainly should be able to do the S of n. So you can extend until the nth term, but you gotta remember that that's not one. We're gonna remember which one was canceled. You can see the cancellation made. This canceled the term, this canceled this term, and then the 2/4 canceled that term. I expect this another term canceled the 2/5. So you can see almost all the term are canceled except that only one. And by symmetry, this term will be canceled by this term, and this term should be canceled by something. That was not right, yeah. So it was like that was supposed to be n-1. So n-1. So it should be canceled by one of the earlier terms. So this one should be canceled. This is the one that remains. So S of n should look like this. So it should be -2 plus 2 plus. Formatting of it. Okay, that page, this is easy to do. Oh, let me scan again, because I remember the earlier one. Okay, that was right. have 21 answer. I hope that the what's showing on the board is showing you the attendance. That should be everyone today. Do you have any questions? We have the test coming up on Thursday. Any questions? Thursday, yes.
Will we have a midterm or will that be our
that'll be like the midterm. So basically, I'm probably gonna combine test one and test two as a midterm grade. So it would be, if there will not be another exam for midterm, everything that we had before the midterm science. I think I'm probably gonna combine homework and exam for the midterm. So midterm grade will be like the cumulative grade by all of the forms. Any other questions? I'm attending a conference on Thursday, so I won't be here to proctor the exam. I'm giving the test two question to another faculty, so another faculty will be coming in to hand out the exam. But since I'm gonna give extra credit for anybody who has done the homework. So on Wednesday, if you want to get extra credit for the homework, bring your homework, so that way I can still add your extra credit point to the test. I'm probably gonna come back and grade the exam once the conference is over. Do you have any questions? So then plan ahead, if you have all your exam, if you already had your exam, if you already have your homework already done and you have it on paper, I can look at it and write down your name for the extra credit points. And you're gonna add extra credit for your test, and then we can do it before the test instead of at the test time. All right, so how many of you have already finished chapter 7? Okay. All right. So just to try to catch up with the chapter 7 homework, if you have some questions for any of the class assignment, feel free to mention those questions. I'll explain in detail on how to calculate those questions, and then we get sufficient practice before the test. So I feel like based on test 1, I feel like anyone that has done all the homework personally, independently, you normally will do fine. Any question?
Sorry, I have another question. So when you're calculating the like work and like the calculations for like gravity and stuff, would that be given to us, or do we have to know like the 9.8 or whatever?
The gravity constant will be given.
Okay.
I think it's 9.8.
Yeah.
I think it's always been 9.8. Yeah. Some tests they have a relaxer pattern. They'll just make a 10. So if it's a 10, it's slightly easier than 9.8 at computation wise. But overall, since when I was learning physics in high school, it has always been 9.8.
That will be given to us. We won't have to.
It will be given, yes. If the question wanted a G, it will be given. The value for G will be given.
So if a question requires we use like gravitational acceleration, it'll be given. on the
Yes.
question.
Yes, that is the solution. Yeah. So if there's no more question, we'll start with what we plan to do. That is continue on with series. I think we're almost done with 8.2. Let's try to look at your remaining topic. Basically, 8.2 is giving the idea what is a series and how do we determine convergence or divergence if we were doing a series. All right, we have some basic idea that for a summation of infinite term, what we can do is to find out a formula for the summation of finite term. And then when we make the number term go to infinity, and we look for that limit, that value of that limit. If that limit is finite, then we see the series converges. If we cannot find such finite number, then we see the series diverge. So diverge could have two reasons. One is the limit add up to infinite large number. Two, it might be it's not finite. It's not infinite, but it's not having a valid limit. So limit does not exist. This should be the reason why the series would diverge. So we have two diverging example at first, and then we went over a special case of series that's called geometric series. Whenever the n is small enough, then the infinite series have a formula that's the first term divided by 1 minus the common ratio. And we also have the formula for the partial sum. You add up the first n term, figure out the summation of the n plus 1 term. That's the formula for this S of n. And then we have a couple of examples. The Taylor-Sophia series is another special case. So most of the time it will be a little difficult to come up with a formula for S of n. We do have that in here for the geometric series. We have the formula for S of n. Then we make n goes to infinity. Then r to the power n plus 1 equals 0. And that's why the infinite sum, when you root the n, s equal to 1 over 1 plus 1 minus r. And that's because this term had the limit value of 0. So having the formulas for S of n made it possible for us to do the calculation for the infinite sum. But there are situations like finding the S of n is difficult. All right, so then we have a couple of special series that we're going to determine. We name this series harmonic series. We will probably mention it again, which is why we started to give it name. And then with that, we also have the alternating harmonic series. This is when the sign alternate, and then the S value actually is a example of what we have in harmonic series. This one actually converge. So harmonic series diverge, but alternating or harmonic series converge. Converge the value of log 2. We're gonna prove it eventually, but for now we just remember the name of the series and know what happened to it. And then a couple of properties we should mention. If you have infinite series, which is summation of infinite number, you get two separate of them. And then there are rules that apply to limit calculation now still apply to the series calculation. So if you multiply the series by a number, that's the same thing as factor. This is a summation. So this is summation is summation of multiple term, infinite term. You can factor C as a common factor, and just do that calculation. Since that calculation for the infinite series is L, so that this multiple rules says this summation of C times AN is equal to C times summation of AN, because L is the summation of all the AN. And so basically saying if you got a constant number, you can bring that out of the summation. So that's really the idea. Very similar to what happened to an integration. All right, the second rule says if you have summation of or subtraction of series, and then basically summation of subtraction or summation equal to summation of subtraction of the summation. This already is summation of the infinite sum. These are something that is similar to what happened to an integration. If you have to integrate summation of two functions, it will equal to summation of subtraction of two integrations. This is the finite. This is the discrete. So infinite sum, integration is infinite sum, and then the series is infinite sum. But what is intercase? One is continuous case. So what we have as improper integral in chapter 6. Now we have a what do you call it? Discrete summation. That was continuous summation. Now we have discrete summation. All right. Some important theory. These are a couple of things we want to prove, and we haven't proved it yet. But right now we're going to write down the formula. The first one is saying that if you are, factorial. Factorial is a number that gets bigger really quickly. So if factorial is in the denominator, then you have 1 divided by a really large number that made a small number. So this is really infinite summation of really small number. Because those numbers are so small, the total summation actually letter the number E. And that gives us another mathematical representation for E. I think we already mentioned that the E can be defined by a limit. E equal to limit of 1 plus 1 over n to the power n with angle to infinity. So we can define the number E with the limit calculation. Now we're saying we can define the number E, not E like 2.718, right? Well, a little over 2.7, but it's irrational, so it's impossible to write the decimal representation. That's why we don't do the decimal number, but we know it's a number. This number also equal to summation of 1 over and factorial, and it goes from 0 to infinity. And in that case, you should remember 0 factorial equals 1 to be there. So that basically means here you have a summation of many terms, infinite terms. It actually equal to this limit. So see, two very distinct things actually equal to the same value. That's interesting. All right, so that's the first one. And then second one, we have if you have 1 over n squared. And we already know 1 over n. If you have infinite summation of 1 over n, like 1 plus 1/2 plus 1/3 plus 1/4, that infinite sum we already know that's harmonic theory. We know that diverge because that summation provides you a number of infinite large value. But then this example 2 saying that change the denominator from n to n squared. Then 1 over n squared is much smaller than 1 over n. Most cases. So we're adding infinite many relatively small number, and this total summation is actually finite. And that value is pi squared over 6. Number 3 is very similar to number 2, except this one has alternating signs. And so you can see that's 1 over n squared, and this is negative, positive of the 1 over n squared. So that one has value pi squared over 12. So by changing the sign from positive terms to alternating terms, this one actually have a slightly smaller value. The value to this value is much smaller than that one. And number 4 is the example of out of the, well, number 6 and number 4, they're related. Number 6 is summation of the alternating harmonic theory. So that's the one we mentioned earlier. And then the value of that summation is natural log of 2. All right, and number 6 is we take out the odd number terms. Instead of n, the n goes 1, 2, 3, 4, 5, 6, and 2n plus 1. It goes 1, 3, 7, 9. So this is only taking out the odd number denominator and then alternating the signs. These two are somehow similar and somehow different. When you lay it out, it's actually pretty different. But as far as the representation, these ones equal pi over 4. Question. We already know that one diverge. So number 5 and number 6 are two closely related theory, and then we give them special name, and then which made it possible for us to keep referring to it now that we have a special name for them. Any question for these series? Come back to it again. So far, right now, we're just introducing them. We don't have to remember how to calculate them, but we're introducing. And then one of the reasons that we introduced them is probably because those values are going to be convenient. Knowing them is a little bit more convenient than not knowing them. So here we have an example. So now that we know these values, of course, you can use all these rules to combine theory and come up with more. So now we have this 1, 2, 3, 4 example. Okay, find those importance theory. I'm going to find out the value of these summations. Out of the 4 example, the most straightforward is number 3. And you can see that was 1 over 16. So this one does not have the summation notation, but you can see there was all squares, right? Summation 4 squared, 5 squared, 6 squared in the denominator. So the number 3 I can immediately see is related to the number 2, right? The second special example. Try to think in my head. Number 2 is related to the special theory number 1. Because you can pull the 1,000 out of it and that will be the E, right? So number 2 and number 3, you can apply the special series quickly and then have it derived. What happened to number 1? It was. We can certainly separate them into 2, right? Subtraction of 2 series, and then maybe. Okay, so let's see how it works. Says evaluate this series. I'm gonna start with number 1. And this you have to change it a little to see how it's related to the special series that we see. To solve this one, what we're gonna do is look at that fraction, see how that could be changed. So we can see this is summation of -1 and then n plus 1 power. And we can write it as n squared over n cubed minus n over n cubed. The cube is the common denominator, the subtraction of the 2. And of course, n goes from. Any questions so far? Do you see why do we change it this way? Separate them. This, if you want to subtract fraction or subtract the numerator and keep the denominators, they have the same function. So this, according to the fraction, how do we treat a fraction? This, put it this. Right? There you go. So why do we change the format? Because now you have to separate series. One is the summation of -1 and plus 1. Out of the first one, we cancel the n squared, you have over n, and then n equal to 1 to infinity. So basically that one you cancel the common factor. And then add the subtraction sign, we have minus, and then you have another one. The -1 to the n plus 1 power is a common factor. Then divided by, see the n cancel the denominator, and then you have n squared. And that's n equal to 1 to infinity. So we're able to separate this subtraction sign, subtract them into subtraction of 2 series. The reason that this will be possible is because of the, well, I moved it too fast. It's because of the second rule, right? The rule says if you have subtraction or subtraction, summation or subtraction, you can separate them into separate. Okay. So normally it would be easier to solve if they're separated. The first one is what we're calling the alternating formula. Right? So this one, according to the special theory that we see, it was special theory number 6. Special theory number 6. It equal to natural log of 2. So this part. This calculation equal to ln2. We'll prove it later in later section, but for now we remember its value. And then there's minus, and then the blue one also looks similar to one of the special series. It's the number 3, right? And we have a value of pi squared over 12. So that's pi squared over 12. Any questions? That's the first example. So basically having those special value already calculated for us, then we were able to simplify this calculation. Moving on to number 2, what we mentioned that we can bring the 1,000 outside the summation as a common factor. This is rule number 1 property. First one, constant multiple rule. If you got a number multiplied to a term in the summation, you can bring this number outside the summation. Bring the 1,000 out of the summation, and we have summation 1 over n factorial, and is from 1 to infinity. Okay, so this is equal to, and you're gonna be careful here because in our formula number 1, it says if you add from n equal to 0 to infinity, 1 over n factorial, the summation equal to e. But right now we're adding from one, start with one, we didn't start with n. So this value actually is 1,000 times it's e minus one, because we don't have the first one. We don't have the n equal to zero term added, right? If you have summation of n equal to 0 to infinity, then the whole summation equal to e. But now we start from one, that means the first number is not added. Starting from one, it look like. So this should be e minus one in estimation. Any question? So that's because one is from n equal to 0 to infinity, the other one is from n equal to 1 to infinity, so that'll be slightly different. Right, so this is that one, and number 3 is a little bit messy. Let's try to read two copies. So number 3, we would grab that question and then like that question only. This summation is equal to, and remember the formula, you have summation 1 over n squared. And then n is from 1 to infinity. And that was a special situation. It was pi squared over 6 if you are adding up square from 1 to infinity. So this is pi squared over 6. Suppose you are adding 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, 1 over 25, 1 over 36, 1 over 49. So if you're adding this infinite many terms, this summation equal to pi over 6. Now back to this question, we're actually adding only the part starting 1 over 16. This number I will be adding. We didn't add the first few numbers. So you're gonna take the pi squared over 6 and then subtract 1 over 4, and then subtract 1 over 9. And that's how we calculate it. And the rest you will probably have to use a calculator since the value itself is rational. I is irrational, these are rational. So it's easier to write that number than having a decimal denominations. Any questions? That's the example number 3. Example number 4, we see it with this. Okay. So how we connect them with any of the formula you had? Maybe we can cancel the n. So n is from 1 to infinity. This is actually n factorial in the denominator, so it's n times n minus 1, and then times n minus 2. And then you keep multiplying until you have 3, 2, 1. That's the denominator. Numerator is n squared, so it's n times n. So what you can do is you can cancel with the n. It becomes this. And then you have, right? And then now you will have n over n minus 1 factorial. Right, and then n is now from 1 to infinity. And we can change this notation. Thinking about what to do with it. We can change the notation to something like this. You can make the n minus 1 equal to m. Then this will be summation m factorial changing variable. So if you call the n minus 1 m, then the denominator becomes simpler. And then since n minus 1 equal to m, then n will equal to m plus 1. So numerator was n, so now numerator actually is m plus 1. And then where do the m starts? M is n minus 1. When n equal to 1, m is n minus 1. M start with 0. So we have m, which is 0 to infinity. Are we okay so far?
So we just did like a substitution.
Yeah, we did a substitution of the variable just so that the denominator will be a little bit more concise. There's another reason to do this because I want to separate the term. Then the first one becomes n over n factorial, and then you get to cancel the n one more time. So it look like this. So then it becomes summation of the two terms, summation of m over m factorial, m from 0 to infinity, plus plus a second one, which is the simply a factorial. It will be a summation of 1 over m factorial, and then m from 0 to infinity. And you can see when you separate them, the first one basically is e. You already write that, right? It doesn't matter what variable we're using. Now you would see the formula. As long as you have 1 over the index factorial, the variable, which is the index, goes from 0 to infinity, that's e. So it could be 1 over n factorial, and from 0 to infinity, it could be 1 over k factorial, k from. So they all have the same calculation, right? Letter doesn't matter. What matters is what exactly was the calculation involved. So essentially this part already is the value e have a summation of e. If you ask what happened to that part, we cancel the m, then you have a summation of m cancel, then you have 1 over m minus 1 factorial, and then m is from 0 to infinity. I don't know what's this exactly equal to. You either write it out or you simplify it, like change the variable one time. But if we that was m factorial, when I change m minus 1 factorial. Yes, after I cancel it, m minus 1 factorial. It's gonna be bad. Right. Shouldn't cancel because m start from 0, right? Be repeat what I was thinking. So yeah, I should take my own device and write it out. So this what looks like m over m factorial, m start from 0, but if m equal to 0, then this will be 0, right? So it's really 0. But you can see what's after this. It will be m equal to 1. So so essentially, when it's 0, it equal to 0 anyway. So essentially, we would start from m over m factorial, and m start from 1 to infinity. Because when m equal to 0, a equal to 0, so there's no point of adding that term. Just adding 0, right? We basically start with 1. So I was thinking about if I have a 0, how do I cancel? All right, only when m is now 0, then we can cancel common factor. So we cancel the m. Now we have a summation of m is canceled. This m factorial is m times m minus 1. So it's 1 over m minus 1 factorial. And then m is starting from 1 to infinity. And then you can switch the variable. This is really a factorial over 1 over a factorial. We can make m minus 1 equal to k, and then k equal to m minus 1. This is really 1 over k factorial, and this is when k start from 0 to infinity. Essentially, I'm saying this is also e. So that summation actually also to that. Any question? So then the total summation here should be times e plus e. At least if I'm starting to solve this portion, that's probably try to find the connection from the formula. We can right? This one, the last one, I do have a little bit doubts. Let's see how they were being derived in the book. I'm trying to keep the message essentially the same. Okay, so it looks like the same. So it's E plus E, so it's 0 2 times. I'm not that confident because I did this question without looking at a solution. Any question? So if you want to see a much more organized patient of it. So at first we would separate the change of variable, and it didn't really display the change of variable here. And keep using the n, but we separate them, and then I was using m or k, but the book just keep using the n. Now we went E, obviously, from this one, after we cancel the n, we have this, and we went back to the variable again. So every time I go from here to here, that's a change of variable. But the book solution didn't change the variable at all, just switch it. There. In my mind, that's you are making the n go to n minus 1 and go to n, that's a change of variable. But we can just call it using the same variable is okay. Any question? All right, so as you can see, it's convenient having those formula. But later in the later section of this structure, we're going to prove those formula. There's one thing we should mention that if you have a series that converge like this summation is finite, then you have to have at least the minimum requirement for it is that if the series converge, then the individual term converge. But the other way doesn't apply. So basically saying if this converge, this will converge. But if this converge, it doesn't guarantee this converge. So basically, if you add many things and the total summation is finite, that means all the things that you're adding is really small. In the expression of that small is the limit of that term, 0. So, in that case, if the limit is not 0, meaning that each term an is substantially large. For example, if the limit there is not equal to 0, then the total summation will be infinitely large. So that as a consequence, if that doesn't converge, then this would be divergent. But that doesn't mean when you're adding small term, they always end up being finite. Because there are situations when the summation of small term. This limit equal to 0 doesn't guarantee that converge, but this converge guarantees it. Any questions? And this is a very quick way. Whenever you say that, hey, this is an, the limit of an is 5, or the limit of an is not 0, then we immediately say the total summation cannot be convergent. Because every term is large, of course, total summation will be large. Okay, so this is when you combine terms, what happens? If you have a divergent series and you might rearrange the term in that series, the result would also still be divergent. So it doesn't like if you move things around, they become somehow convergent. That never happens. So you can have like 1 + 2 + 3 + 4 + 5. The total sum is infinite. But if you rearrange the term like 1 + 20 + 1 + 31, would that total summation be finite? That will never happen. The convergent divergent nature doesn't change. The second one saying if you have a convergent series, it will remain convergent even if you change a few terms in there. Oh, this is the not what I realized I was talking about two different things. All right, basically it's saying that the infinite summation the nature of it happened with infinity. So if you only change a few terms in that theory, it doesn't change the convergent or divergent property. So it will staying the same. That's why whenever we talk about convergent or divergent of the theory, we look at behavior at the first few terms, but then you can remove a few terms and look at all the other terms, and then they will still have the same property, even though the total sum are going to change. The convergent divergent property doesn't change. We actually apply that, for example, the situation we're adding from 1/16 plus 1/25, 1/32. So we really didn't start from 1/, we didn't start from 1/4, 1/9. So you can see it changed the total summation, but the total sum is still finite. So if you add up 1/n squared, the total summation is finite, then changing 1 or 2, like change the first few terms, didn't change the nature of the convergent divergent, but it did change the value. It changes from larger value to a smaller value. Okay, so then this statement basically saying if you only are changing a couple of terms in the theory, it doesn't really change the overall convergent divergent behavior. And that will be the last page. Overall, this section 2 is focused on explaining the concept of a theory, and also maybe have some of the elementary example of how theory can be calculated, or what was some of the popular rule applied to calculation of theory. And about section 8.3. So we're gonna now start looking at individual type of theory and how do we figure out converge diverge with more systematic method. Okay, 8.3 called integral and comparison test. So we're actually applying a little bit calculus now. As you remember, section 8.1 and 8.2, what we did is a lot of others are arithmetic and with a little algebra. There's not a lot of calculus. Maybe some limit idea. Limit idea is calculus, but most of it doesn't involve integration. So now we're gonna look at how do we apply integral to a theory, calculation theory, on integral and comparison test. Okay, so what's a comparison test? It's one of the methods to determine whether a theory is divergent or convergent. And that's why it's called a test. After you run the test on the theory, you can determine the theory diverge or converge. Okay, so in the test method itself, we'll do calculation of integral. All right, we're gonna start with the integral test. It's just like the name. We will convert the summation of the infinite theory into integration formula. What we're saying here is that remember the difference between a theory and a function is that a theory has its domain being all natural number, but a function has f of x, and x is a real number. Real number is being defined on the interval, and then the sequence or theory only being defined for natural number. So here we're saying one is discrete, one is continuous. They actually have the same converge behavior. So we see the summation of n from 1 to infinity converge if and only if this 1 to infinity of the integration of the function ax converge. So we're trying to define it on the number set in 1 to infinity. Now we don't care about 0 to 1. But all natural number are 1 or bigger. Okay, when we say even only if, meaning that if this one is finite, then the integration is finite. And vice versa, if the integration is finite, and then the summation is finite. So we can go back and forth. Any question? This method provided a way to determine if a theory converge or diverge. You might ask, why don't we apply it all the time? We actually have a couple of different tests. We cannot apply this for a couple of reasons. Sometimes you will have a function that cannot be defined for all real numbers. For example, factorial. We can calculate factorial, like, but normally factorial are only being defined natural number or number bigger than zero. So n factorial. It means that you start with n and then times n minus one times n minus two until you reach 3 times 2 times 1. So for example, 5 factorial equal to 5 times 4 times 3 times 2 times 1. Okay, so the nature of the definition require us n factorial where n gotta be a natural. Okay, so then, for example, the earlier question, we have summation of 1 over n factorial. We now know that that's e. But in order to prove it, can you integrate 1 over x factorial dx? It's not very likely, and we don't have a actual definition for x factorial, have x being a real number. So for example, 0.5 factorial, what does that mean, right? So because there are things that are not defined, but that are defined normally, only defined for natural number. Therefore, there are the kind of situation. It works out with the theory, but it doesn't work out as an integral. So this test is very useful, but it's not going to answer all the questions. But we're going to try to look at a couple of situations where this is possible. All right, actually, we try to fill the gap. The fraction factorial, I think we had a gamma function. Try to define the factorial of a real number. That was a integration define function that went into another collection of problems. But anyway, right now we're just looking at n factorial as a factorial of a natural number or 0. Okay, so let's try to understand the underlying logic why this is true. What we're going to do is actually make a comparison between this and this. But then this is the infinity, that's also infinity. It's a little bit hard to compare them without putting a rule on this. So what we're going to do is we actually are looking at from two different perspectives, and you see two different pictures here. One is we will calculate the you can compare the summation n equal to 1 to 1 to infinity of a n using the red block in the picture. So over here, we're looking at area from the integration and area related numerically to the summation of series. So the one on the left, you see if x equal to n equal to 1, if n equal to 1, then we have a1. So then the height, this is a1. All right, the height is the size of the an, and here from 1 to 2 is 1, right? So the area of the first rectangle is a1 times 1. The second one is n equal to 2. So the height is a2, and that's a2 times 1. So that's a1 plus a2 plus a3 plus a4. So all the rectangle on the left picture is the summation. All this can go down n from 1 to infinity of all the an represented by the area of the red rectangle in this picture. Are you okay? Height or length times width out of every rectangle. Now area, the integration on the right, integration is the blue curve of ax. The curve represents ax. That's why when x equal to 1, that's a1, that's a2, and x equal to 2. All right, so what we're doing is we're going to find area from 1 to infinity below the blue curve. If you can see area from 1 to infinity below the blue curve, that is the total area of that 1 to infinity is actually smaller than all the rectangles. So the picture itself proves a special situation when the summation of AX is less than the summation of AN from 1 to infinity. Any question? And we're gonna try to prove vice versa. Why did this work? Because we purposely made a point to draw the function an as a decreasing function. Just imagine if the function goes this way, it might not be true. But we know for sure that an as a convergent theory, an will be decreasing. At least in this picture. All right, over here, we're saying, suppose an is convergent, so it's a decreasing curve. And now we're gonna not start from 1, let's start from 2. So x equal to 2, have a2, and a2 and a2 are the same. The a2 on the integration is a parenthesis 2 parenthesis. A parenthesis 2 parenthesis is a2. They're essentially the same thing. We're hypothetically thinking an as a function ax when x being a variable. So here we have x-axis on the horizontal line. We find number 2 and go to the blue curve. We have a2 in the height of the rectangle. So the first rectangle is a2 times 1, and then the second rectangle is a3 times 1, a4 times 1, and a5 times 1. So the summation of all, you can keep going. This also picture can go on and on to the right. So this, the red rectangle area is a summation, the value of a equal to summation and equal to 2 to infinity. Any question? So this one is less than the, you can see the area of the rectangle is below the blue curve. So if you're integrating from 1 to infinity, that total area is the area below the blue curve, which is slightly larger than the area of that summation. Summation of that. Are we okay? So we're saying this. Now, number 1, if the series is convergent, then this is convergent, right? So according to the left side equality, if the series is convergent, then since the integration is less than the series, so the integration would be convergent, right? And this is saying that series converge, then the integration converge. Now, according to the right side picture, it's saying suppose the integration converge. So 1 to infinity a of x dx is finite. And according to the right side picture, then summation of an from n equal to infinity will be smaller than that integration. Since this is finite, integration is finite, so the series is finite, right? Right? And then remember, for the series, it doesn't matter what happened to a1, as long as the infinite term is finite, right? So that concludes this idea that series converge, integration converge, series converge. So they converge at the same time. Another statement is they would diverge at the same time. For example, if the integration diverge over here, if the integration diverge means that integral is infinity. If integral is infinity, and then the series is bigger than the infinity, right? According to the left side picture, the series will also diverge. Okay. Another thing is, what if the series diverge? I mean, according to the right side, the series diverge. This is the infinity, and then of course this integration is bigger than the series, that will also diverge. So they will cause each other to diverge and converge at the same time. Any question? Great. So that's really the logical reason why I would say that they would, even only they will converge and diverge together with each other. All right, for example, so here we have a question. The question is determine the convergence of this series. You know, we don't want to calculate it. We just want to know whether it's a finite or infinity. So this section is 8.2. The whole point is you have to know there's an answer before you go ahead and calculate it. So according to the integral test, you run the integral test, and then now you find out it's divergent. And then now you will see the series divergent. There's no point of calculating it. Now, if you run the integral test and you know it's finite, and then you know they're not going to be the same, right? Back to that logic. If this is converged and this is also converged, but they don't converge to the same value because right? You can see the from picture, they're not always gonna be the same thing. But at least it will be finite or infinite at the same time. So we'll determine whether it's finite or not. If it's finite, we're gonna go ahead and calculate it. And calculation and determination of the convergence is not always the same thing. All right, so we're gonna run the integral test and determine if this is a convergent. And then that's where we're gonna do more calculus, integral calculation. So we're gonna turn this to integration first. So we'll integrate from 1 to infinity. Then change that into x. So ln of x over x squared dx. According to the integral test, if this integration is equal to a finite value, right now, value, yes. If it equal to finite value, then this summation also equal to finite. They will both converge. If this is equal to infinity, then that summation also equal to infinity, and of course it will diverge. So how do we calculate this? This is something that we've done in chapter 6. So how do we do the integration? How do we integrate out of x over x squared? The method is called integration by part. Yes. So we're gonna do integration by part. We will normally have the integration, keep the ln of x as u, and then this is gonna be our v. So I'm trying to write u dv. That was x to the -2 power. Try to find nth derivative. That will be the -1 over -1. This was the derivative, right? We want to write a dv, so v would be this. Okay, so that's now in the format of u dv, and then the integration is going to be uv, and then we have -1 over x, -1 over x ln of x. That's u times v minus integration of a du. V is negative over x. And du, this is a u, so that would be 1 over x dx. Du, this is a v, du. So according to the calculation, you can also run your method. So I'll start. Try not to write too much u and v in the middle of the process, but if you're used to write u and v specifically, it would be okay. So this is equal to negative cancels plus integration of 1 over x squared. That the answer is -1 over x. So that's the antiderivative, and we were supposed to put in the integration limit. Now we put it in the number calculation. So we're going to calculate the value here. And the upper limit is the limit value. If when x goes to infinity, log reason infinity over infinity, 0, and 1 over infinity also equal to 0. At the upper limit is 0. At the lower limit, when x equal to 1, logarithm 1 equal to 0, ln 1 equal to 0, this is 1 for 1. So I can see this limit, this value equal to 1. Equation. Any question? So they equal to 1. We can certainly confirm this. There are calculation tool. You can use Symbolab, or you can use that function calculator for a few calculation tools here. One of the ones is function calculator, and see if that works. What we're gonna do is we take natural log of x divided by x squared, and we're trying to integrate a to, I'm not sure. First, so I'm not sure putting integration limit at infinity if that works. Okay, so that's the antiderivative as we had over here. It's the same antiderivative. Maybe you can, it says type infinity over infinity. Maybe we can do this. The lower limit is 1, the upper limit is infinity. has failed, it's improper integral. It's verified as well-defined integral. Okay, so obviously it won't affect. So it's diverge. I see. So I still feel like the limit should be one because I put a really large upper limit there that's like almost one. So I think, and as the x gets bigger and bigger, the limit should be roughly one. You don't see a large number there, so I think. So this computer do not do calculation of infinity for us. It will. It's a human idea that is the improper integral. Most of the calculator will only accept a finite number as the upper limit. If you have to calculate improper integral, you have to do that limit calculation yourself. So it looks like this one converge, right? We have the integration have a value of one, so therefore this theory also have a finite value. The one is a finite value, so this summation of theory will be a finite value. So we say according to the integral test, this theory converge. Any question? So what's being called integral test is using integral as a determination tool. So it's not a computation tool, it's a determination. And that's why I do recommend whenever you have this kind of situation, you can quickly finish the computation. So even though I did carry out the calculation, the integral it's not entirely the focus. The focus really to understand the idea, get to that value quicker. I wonder if you run the symbol lab, you might be able to find out the answer a little quicker. Okay, so this is our first example. We will calculate the integral to determine if it's converged. We don't know that it's converged. I believe the summation is it's not like the one should be smaller than that. All right, so anyway, so applying the integral test, we can come up with a couple of the pattern. So far we have a couple of special theory already, and we're gonna define something called P theory. What's a P theory? It's P as in the initial letter power. So you have 1 over a power function, and that power in the denominator, it kind of determines whether theory will converge and diverge. So here we can see a P theory is a theory of the form. It's a special form of theory. And below we have a general P theory that, but it could also be an plus b to the power p. So that's power theory, and this is a general P theory. So we define the special term, a special name that's called P theory, because the value of P often give us a quick way to determine whether the theory will converge or diverge. So here is our rule. If you want the theory to converge, you have to have a power of the letter P. It has to be bigger than 1. So you might wonder bigger than 1 by how much, like P equal to 2, P equal to 1.1, or P equal to 1.5. The answer is any power that's bigger. It cannot be 1 because we know if P equal to 1, it diverge. And the theory that we already tried, such as summation of 1 over n. So you have summation of 1 over n. That was a notation. N goes from 1 to infinity. The actual calculation is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. You're gonna start trying to look at when you see this, you know it's this actually. This is called harmonic theory. We already know this is diverge. So now the rule here is saying that we want that power to be bigger than 1. So obviously, if it's 1, if they're all power 1, we already knew that was divergent. So the P, as long as it's bigger than 1, is fine. So a quick example may be It could also be 1.5, which is like 1.5 of power with a root calculation. You can have a summation of 1/n. That we know diverge, so it could be like 1.1 and then n is 1 to infinity. And this basically equal 1 plus 1/2 to the 1.1 power and plus 1/3 to the 1.1 power plus 4 to the 1.1 power. Anything that has a power slightly bigger than 1, that's all you need to have this. This is a conversion. And that rule basically, based on the integration that we were talking about, for example, if you integrate like 1/ax plus b to the power p theory, this power dx. If you integrate this, you will have an antiderivative based on the power rule. The antiderivative, this is negative p is negative p up to -1. So then the answer will be ax plus p to the power of negative p minus 1 over negative p minus 1. Integration, we plus 1. So then this is what happened. This is the reason why we want that p to be bigger than 0, because this is the 1 minus negative p 1 is a power. If this power, we want this power to be negative, be less than 0. That way, when this power is negative, then the limit of the numerator, we calculate it at infinity, we have 1 to infinity. So we're gonna find the limit value of this at infinity. Limit of this term, ax plus p, when if it's negative, it will be a reciprocal, like 1/p minus 1. Okay, if you turn this to the denominator, it will be negative, and then when the x go to infinity, this will equal to 0. Suppose p is bigger than 1. So if p is less than 1, we have a problem. If p is less than 1, then 1, this is 1 minus p. 1 minus p, negative p plus 1 will be positive. And this will be in the numerator, right? You'll be calculating ax plus b to the power of 1 minus p. When x is going to infinity, this is infinity, right? Diverge situation. So we were trying to limit, make sure p is bigger than 1, because we want to guarantee that at infinity, the limit value actually equal to 0. This is what we're trying to do. It will only works if p is larger than 1, because that one would be positive in the denominator, but negative in the numerator. So this will be negative, because this is positive. Any question? So this is the rule. We just want the power in the denominator to be bigger, so the whole fraction will be smaller. The whole part. Okay, so we have a couple of situations when knowing the key theory rule, knowing this result will be more convenient on determining converse diverge. For example, we know this first one, right? First one diverge, and then let's look at the second one. This one converge. I also remember the value was pi squared over 6. Number 3, diverge or converge. Diverge is 0.5 power, right? In the denominator, he has to diverge because the p is too small. This one, we know that was alternating harmonic theory, right? Converge. Converge. But that's not because of the rule. This is alternating. It's not the. That's another thing about the rule. The integral test only works if we have positive terms. So if you have alternating term, we're looking at different type of problem. Number 5, see the power. So it converge, it's bigger than 1. And the last one, diverge. It diverge because it's geometric series, yes. There's a common ratio equal to 1/2. It's an exponential function, actually, so it's geometric series. So these are for special example. So some of them are applying the P series rule. Some of them, like this is geometric series. Some of them we actually look at the harmonic series and it's a variation. So we're start to accumulate different scenario when you determine whether series converge or diverge. So it's better we put them down and somehow remember those special cases. Let's see. All right, and then there's a second rule called the comparison test. As you can see, we actually are not just talking about the integral test, we have comparison tests, and this is called direct comparison test. We also have the limit comparison test. We want to compare the series in order to determine the convergence divergence. So why do we study this one? Because we already have a couple of special theory that we know diverge or converge already. So maybe when we see newer theory, we can apply what we know about the older theory. Now we can compare them with newer theory to determine whether they are convergent or divergent. So basically saying, suppose we have two theories that are comparable. Let's suppose one of them is bigger, an smaller than bn. So according to the conversion test, so if an is less than bn, then summation of an will be less than summation of bn. Now, the number one says if bn is convergent, meaning that summation of bn is finite, as a consequence, summation of an will also be finite because you're smaller than the finite number, of course, your cell will be finite. And then the second rule saying, since an is less than bn, so summation of an is less than summation of an. Now, if an diverge, meaning that an is infinity, we're talking about positive terms there. Summation positive term, when it diverges, the only reason for summation of positive term can be divergent is that total summation is finite. It's infinite. So summation of A is infinite. Now summation of Bn is bigger than the infinite number. Of course, itself will be divergent, will be infinite. So those are rule 1 and rule 2. We can see that when two terms can be compared, then their summation can also be compared in the same direction. And that comparison will cause them a conclusion about the conversion. Right. And this is something which would be useful. For example, this one. You can see we have denominator and you want to compare with one of them. And obviously this is smaller. We can relax this. You can relax it whichever way, as long as we found something to compare it to. And here is my idea of comparison. For example, I know for sure that the denominator is smaller than the fraction gets bigger. So instead of having two terms in the denominator, I say keep this. All right. So obviously the one on the left is smaller because the one on the right has smaller, right? The more you have in the denominator, the smaller the number. So I know this one definitely converge, right? We know that one we already studied the beginning. So because this comparison, we have this summation of this will be bigger than summation of this. According to what we learned from last section, this is equal to a finite number, which is like pi squared over 6. I know that's finite. Now that means the infinite summation over here is less than a finite number. So itself will also be finite. We don't know what it is. We know it's definitely a finite number. So we know that's convergent. So having the comparison made it possible for us to relax it, and I have an answer for some quick determination. That'll be it for today. And then work on the homework assignment for chapter 7. Let's try to finish the whole chapter. We'll be ready for the exam. Thank you. See you tomorrow.
Yeah.
Why you putting it up here?
I'm doing what? Wait, give it like, yeah. What? How many?
Where can you have a contract? Hey, further.
Oh, that one doesn't have the outbreak and so the integration of it, I think it has a value, but it's not,
It's like a. Hey.
it looks like a bell curve. So if you integrate it, it is finite. We don't have a formula. We can calculate it. Like if you only calculate you want to find a formula for the integer, we don't have it. But if you want to just calculate 0 to infinity, like you want to know what that number is, because the nature of it's small enough as infinity. So you integrate from 0 to infinity, it would be finite. And I think it would take pi over 2 or something. It can be calculated. I think we got a formula, we got a method for in Calc 3. We would use the double integral. So you do integration of e to the negative y squared dy 0 to infinity. And then we combine them and turn them into e to the negative x squared minus y squared dx dy. And that's where now we use polar integral. So we have a message treated later when we learn double integral. Right now, calculated by itself, there's no formula. Huh?
What's the coverage?
Oh, chapter 7.
All chapters.
Oh, chapter 7. There's no chapter 8. Yes. So I keep asking questions because I want to make sure that we're ready for the test.
Thank you.
Thanks, James.